Okay, so we're ready to start looking at Module 8, which is our last module in this course, and we are going to be focusing on CAM design. So as we look at our module here, the first thing is going to be our learning plan. We're going to find our PowerPoint presentation there. We're going to be looking at Chapter 9 in our book, and then it kind of we can grab the sections that are going to be most important for us. Session recordings, I'm recording this session. I'll be uploading this later this evening, but there's the session recordings that are out there from previous offerings of this course if you wanted to look ahead at that. Practice problems. There are just a couple of practice problems here, and I believe we get through these tonight in the work that we're going to be doing, but we'll kind of confirm that as we go along. Then you're going to notice that assignment number 8. So there are 4 problems in assignment number 8. Now, what I have done, oh, I didn't do it yet. Let's do it right now. So you'll notice that there are 4 problems, 20 points each. There's some calculations, but then there's also some CAD work, and it takes a little time to do them. So I didn't give you a ton of them. But what we're going to do, I do this in my other course too. Since this is our last module, I am going to make the number of points for this module 40, okay? So you can do one of 2 things. You can either pick 2 problems that you want to do, okay? You can pick, one of the first 2 and one of the second 2 because you're gonna find out how they're different, okay? So you can't do the first 2 and be done. If for your 40 points, you have to pick one of the first 2 and one of the second 2. They're just different problems, different things that we're going to be doing. And it'll make more sense after we start looking at stuff or getting done with what we're doing tonight. Or you can do all 4 and get a total of 80 points out of 40. So it's kind of like extra credit if you do more problems. Okay. So I know when we get to the end here, many times students have probably other courses and you're kind of, getting to, running out of time, if you would. So I'm trying to help you out where you have to at least do one of each type of problem, but you can reduce the number if that seems to be better for you. Or if you have extra time and you're like, I don't want to miss anything in kinematics. I want to get my money's worth. I want to make sure I know everything and I know it well. You can go ahead and do all 4 and then you get extra credit because you've gone, above and beyond. So I'm going to let you decide how you want to handle that. But know that there's 80 points total here. It's going to be out of 40, but again, don't just pick the first 2 and be like, I'm done. Okay. You need to have one of the first 2 and one of the second 2 minimally for your 40 points. Does that make sense? Then it gives you, there's 2 different types of problems. So, okay. Any questions on that? It'll make more sense when we kind of get done tonight. All right. So what I'm going to do is I'm going to go back to our module and we are going to take a peek at our PowerPoint presentation. So I'm going to go to my learning plan and I'm going to open up the PDF. So chapter 9, we're going to be looking at CAMs. I think it's kind of a fun unit because we're going to be ending with some CAD work, and usually students enjoy doing that. There'll be some computations, but the CAD work is kind of fun. So our objectives here are really to look at CAMs and followers. They're an integral mechanical, type of a mechanism, truly, but they work a little bit different than some of the things that we've seen thus far. The 2 main things that we're going to be doing is we're going to be constructing CAM follower displacement diagrams, and we're also going to be constructing the profile of a disc or a plate CAM to go along with a displacement diagram. So these are the 2 main things, but we're also going to be looking at some different types of CAMs, different types of followers, so you can kind of see how things can get integrated into designs. So the introduction here first. A CAM accepts an input motion and it imparts a resulting motion on a follower. So if we look at the very first page that we have in this chapter, I'm going to go over here. On page 223, this is the first page of chapter 9, you will notice that we have an engine valve train schematic here, okay? And what we have is at the very top, we have a camshaft, which is in contact with the rocker arm, which then is going to impart motion on our valve stem. And then that's going to open and close the combustion chamber, okay, down in the engine. So what we're interested in this particular chapter is going to be this arrangement with the cam, and in this case, the rocker arm, which is referred to in more generic sense, it's going to be the follower. Okay. Now, what happens is that cam is going to rotate, and its center of rotation is at the center here. But you're going to notice that there's kind of this irregular profile, or what we would call a lobe, kind of sticking out. As that lobe rotates, what's going to happen is, since this rocker arm is in contact with the profile of this cam, it's going to follow that. So this is called a follower, all right? So as it follows that profile, you can see when that lobe rotates, it is going to push that rocker arm down, okay? Which then imparts a downward motion on the valve stem, which is then going to push open the combustion chamber, if you would, okay? Then as it continues to rotate or goes past that lobe, it's going to go back up as it follows that profile of that cam, and then that valve stem is going to move along up with it. Something about a cam follower, or a cam and a follower, is that the follower, in order to impart the motion, has to be in constant contact with that profile of that cam. So that's why we have things like springs that keep things in contact and such. As part of this course, you will not be designing the different elements. What we're going to be doing is looking just at the displacement that occurs on this follower. What is the motion of that follower that we need, okay? And we're going to be looking specifically at displacement diagrams, but then also creating the cam profile. I notice that this, so, oh, Brett, okay, so if all four, oopsie, sorry. If all four are done, you would get 80 out of 40, correct. So it's kind of like 200%. So kind of like a built-in extra credit. So yeah. All right, so now let's go back to our PowerPoint presentation. And that's a very common use of a cam and a follower setup. So as I said earlier, a cam is going to impart that motion on the follower itself. So everything starts with the cam. That's where the input comes. So however that shaft is being driven, that is going to impart the motion, and then the follower is going to do what we're asking it to do. It's used to obtain unusual or irregular motion that needs to be timed to the rotation of, in this case, like a camshaft, okay? Cams are used in factory automation because they sequence displacements in a very cost-effective manner, okay? Instead of having to program a servo motor or something like that, this is a very simple setup. I mean, it's pretty mechanical, but if you just need something to be timed with the rotation of, in this case, that cam profile, it's very easy to achieve, okay? So they're quite popular for those types of uses. So let's look at different types of cams. So the most popular, and the one that we're going to be looking at, is going to be the plate or the disc cam. So if we look underneath on page 224, in the bottom of our first column, right here, this is going to be a plate cam, okay? And the cam is going to rotate on center right here, and then you're going to notice kind of this irregular profile, okay? So that's what we call the cam profile. As this rotates about this center, as you can see, this lobe is going to rotate up. It's going to push the follower up and down as it stays in contact with that profile. So plate or disc cam is what we call this. The next one is a cylindrical cam. A cylindrical cam, you're going to notice it's on a cylinder. There's a groove, and the follower then follows that groove in and out as the cylinder rotates, okay? And then the last type that we have here is going to be a linear cam. So we have a cam that's going to go back and forth. It's a plate with a groove in it. And then the follower has a pin, so that as this goes back and forth horizontally, the cam is going to go vertically back and forth as well. So, or up and down, if you would. Now there's different types of followers as well. So if we look on that very same page over to the right, we're going to see a couple different types of follower arrangements. Now, first of all, we're going to look at the follower motion. The follower motion can either be linearly. Okay, so in the case of the two that are on the left-hand side here, the followers are going vertically, but they could go horizontally as well. They don't have to go vertically, but in this orientation, they're vertical, and so is this one. Over on the right-hand side, these are pivoting about a center. So as you can see, we have the roller, and it's gonna pivot around the fixed center right here. So as this cam comes around, it's actually gonna pivot on a radius rather than going linearly up and down or horizontally. Okay. As far as the follower type or shape, there's a couple different ones that we see here. A common but not used very often type is going to be a knife edge. And all that is you're going to notice that there's a point. It comes in contact with the profile of the cam, and it's simply going to move up and down as the rotation occurs. The reason that this one isn't used all that often, especially not for high-speed applications, is that because there is point contact, that point can wear away pretty easily, as well as it can cause like wear around the profile edge. Okay, so it's not used all that often. If you're going to use something that you want to get friction or surface-to-surface contact with, having something like a flat or a spherical edge on the end is a better option than just a pointed type of what they call a knife edge. Another popular one is going to be a roller, actually probably the most popular one. And the roller offers the ability for the surfaces to roll relative to one another with relatively low friction. Okay, so you don't have a lot of resistance. So that is going to be a popular one as well. And actually the two assigned cam profiles that you have are both going to be roller followers. So we looked at follower types and we looked at follower shape. Now, motion sequence, okay, motion sequence. So follower motion, when we specify how we want a cam and a follower to work together, what their end result or their final function is going to be. We start with the end in mind, and the end in mind is the output of the motion, and that is going to be the follower. So what do we want our follower to do? Okay, so that's what they're talking about here. What are the prescribed motions? Now, you can have translating followers, as we saw earlier, where they're going vertically or horizontally in a straight line as they rotate, as they're in contact and rotator, and that cam rotates around. Or you can have those swinging or pivoting ones. Really just depends on your application, and as the designer, you would choose those. We are going to be focusing on the translating ones. Follower position, inline or offset. As we look at the linear application of the follower, which are the two on the left-hand side here, as we look at the travel of that follower, we're going to take the center line of that travel of that follower, we're going to extend it down. If it intersects with the center of rotation of the cam, that is what we call an inline follower. Okay, and that follower doesn't have to be a knife edge. It can be a roller if we wanted to. It can be a flat face if we wanted to, or a spherical. Okay, it's just that the travel is going to be in line as we extend it down through the center of rotation. So that's an inline follower application. Offset is going to be what we see directly below. So you're going to notice that we have the center line of the travel here. And if we extend that down, it is not going to intersect with the center line of that cam. So this is going to be an offset distance, okay? So you're going to be doing, if you choose to do both of the cam profiles, the last two assigned problems, one is going to be an inline and one is going to be an offset, okay? And I'll be showing you through our demonstration time how to construct those. Okay. Follower shape. So we've already talked about the different shapes. There's knife edge, roller follower, There's the flat face and the spherical face. And really what it comes down to is the final application, how fast it's rotating, and what you are looking for in the end. A lot of times it comes down to minimizing the amount of friction, especially between the cam profile and the follower itself. So roller followers end up being the most popular that we see. But these other ones are out there and they can be used, but you just want to, make sure that it's appropriate for your application. So I'm not going to spend a whole lot of time there. Prescribed motion of our follower. So when we look at the motion of our follower, that is, as I said earlier, that is our end result. That is going to be our output. And that's where we start with our design. So once we know what we want that follower to do, now we start to break it down into how much time does each one of those prescribed motions take, okay? So we're going to have to find out what is the total amount of time required to complete a full cycle so that the full motion of the follower is realized. Now, I've been kind of saying some of these things, but I think it's a good idea to just take a quick look at what a cam and a follower kind of look like or operate like, so you get a little bit better perspective as we're going through things. So I like this little short video. Oh, we don't need the music. I'm going to turn that down. But as you can see here, you're going to notice as that cam rotates around and that lobe comes in contact with the follower itself. So the follower is the vertical. This is a roller, a type of a follower, and notice that it just goes up and down as that lobe comes around. So one cycle is going to be one revolution of that cam. And what that does is it times out when it goes up and when it comes down, when it goes up, when it comes down. And that's all going to be controlled by how fast that cam rotates. Okay. Let's go. Another one is this one. Here it has a little bit different profile. So you can see that this one stays up for a little bit and then it comes down. And then it stays up for a little bit and it comes down. So the shape of the profile can be vastly different and unique for each type of roller and cam setup. Okay. Here's a knife edge one. You can kind of see. See, I can't get it on my screen. Hold on. Yeah. And again, it's not that they can't be used, but just know that you're probably going to have wear quicker on the edges and such if you use that knife edge. So just a couple examples of what a cam and a follower arrangement may look like out in industry, if you would. So when we look at a cycle, like I said, that is going to be how much time it takes to go around one revolution. Okay. So when we look at what that cam or what that follower needs to do on its output, we're going to be breaking it down into different segments of time. So there's going to be a total time. That's what the summation symbol is here. And that's going to be equal to time for the first segment of motion plus the time for the second segment of motion plus the third, and so on, however many segments of motion there are in one revolution of that cam. Then we want to calculate what is the required angular speed, W, of that cam. And basically it's just saying, okay, I need to complete one revolution in a total amount of time of the motion that we need. So it's going to be divided by the summation of the TIs, okay? And then lastly, we want to calculate the number of degrees per individual motion. So we're going to take that angular velocity and we're going to multiply it by the individual time segments so that we can find out, okay, segment one, how many degrees of a full revolution does that take up? And that's going to be called beta one. Then now let's look at segment number two. How many degrees of one revolution does that take up? And so on. So, and then by the time you add up each one of the individual motions, that should equal about 360 degrees or very close to that. Okay. So what I want to do is, before we get into a problem, let's just kind of write these couple of equations down so we have them handy. And then we're going to do our first example because, gosh, the last time I was together, it sounded like some people were disappointed we didn't do an equation sheet. So I don't want to disappoint anymore. This is our last week. Get one more in, right? All right. So this is going to be CAM equations. And honestly, there really aren't many, just those couple. But it's good to kind of organize them and make sure we've got them all in one spot. So total time, capital T sub I. This is simply going to equal the individual times of the different segments of motion. So it's going to be time 1, time 2, time 3, okay? And all of these are going to be in seconds. So the units are going to be of time are going to be seconds that we're going to deal with. Because again, it's one revolution. You wouldn't really do it in minutes, okay? The next one is going to be the angular velocity of that cam, okay? And that's going to equal the change in our degrees, if you would, but we're going to simplify that in just a second, divided by the change in time. For us, we're going to always look at the angular velocity of a cam. How much time does it take for one revolution? So we want to take a revolution per the total time for one revolution or cycle, okay? So again, total time to do the full prescribed motion, by adding those all up, that's one revolution of our cam, okay? And then the last one is going to be cam rotation beta, okay? Beta I is going to be equal to, and that's gonna relate to whichever segment of time we're looking at. So we're going to take the cam rotation times however much time we're taking up for a segment. So if we're dealing with segment number 1, that's going to correspond to beta number 1, okay? Or cam rotation for that time number 1. 2 is going to be beta 2. 3 is going to be beta 3, and so on, okay? All right. So let's take a peek at our first example to kind of ease into this process. So the first example we're going to be looking at is going to be example 9.1, and this is on page 226. So I'm going to zoom in here, okay? Kind of get the picture on. And it says a cam is to be used for a platform that will repeatedly lift boxes from a lower conveyor to an upper conveyor. So our cam is going to be a lift. So on that lift, this is where the box is with the dotted lines. It's starting at the lower one. And as you can see, as this cam rotates, this is going to be then pushed up to go to an upper conveyor. And then maybe something else is going to push it onto the conveyor. So then it will come back down in that sequence. Okay. What we want to do is we want to plot a displacement diagram. We're going to look at a final result of. We'll get an opportunity to plot, but for this first example, we're going to kind of ease into it. So we're going to look at the displacement diagram and determine the required speed of the cam when the follower motion sequence is as follows. So down here, you're going to be given in your problems a sequence of motion. So the first thing is we want to rise 2 inches in 1.2 seconds. Okay, so that's the first step. So that means that we want our follower to go up, okay, 2 inches, and we want to take a time of 1.2 seconds. Then it says we want to dwell. All that means is we're going to stay in that spot for 0.3 seconds. So we're giving it time for something to push the package onto the conveyor on the top, okay? Then once we dwell for 0.3 seconds, we're going to fall 1 inch, okay? And in that time, it's going to be just 0.9 seconds to do that. Then we're going to dwell another 0.6 seconds, and then we're going to fall 1 more inch in 0.9 seconds, okay? Now, however much you rise, you have to fall, okay? You can't have a gap there. So always make sure that if I rise, in this case, 2 inches, that I fall 2 inches, and it did it in 1 inch increments, okay? So no, you don't have to do the whole thing on the way back. You can segment it out. And then, like I said, the dwells just mean that we're going to stay in that position for however much time. So the first thing to do here is to determine what is the total amount of time that we're taking in one revolution. So these 5 steps is one revolution of that cam, okay? So as we look here, I'm going to put my equations away, zoom out a little bit. So this is example 9.1. And I'm not going to redo the instructions. I'm not going to rewrite that. So I'm just going to put, we need to find, okay, W of our cam, okay, and then each one of the betas 1 through beta 5, okay, given the sequence that's in this problem, okay, 1 through 5. So our W of our cam, okay, if you would, our W of our cam is going to be equal to 1 revolution divided by the total time for the operation of this cam. To find the operation of the cam, the time that it takes to operate the cam, we're going to take these 5 times and add them all together, okay? So we can say that the summation of our times is going to be equal to T1 plus T2 plus T3, T4, and T5. And there's 5 times because we have 5 sequences of motion in one revolution of that cam. So if we look back, T1 is 1.2 seconds, T2 is 0.3 seconds, T3 is 0.9 seconds, T4 is 0.6 seconds, and T5 is 0.9 seconds again, okay? So the total amount of time to do one revolution of our cam is what? If we add those all up. What do we get? 3.9 seconds. Yes, that sounds correct. Anybody else get that? Okay. That is going to be the number that we put in the bottom of our equation here for the rotational speed of the cam. Okay. So I'm going to now do my W of my cam. That is going to be equal to 1 revolution divided by the 3.9 seconds. Okay. So I'm going to get 15.38. Oh no, I'm so sorry. So sorry. That's not right. Somebody tell me what my number is. 1 revolution. What do you get? 0.256. 0.256 revolutions per second, right? Okay. Now, if I was telling somebody what the angular velocity of my cam was, I would probably give them in revolutions per minute, right? So we'll do a quick conversion. So our 60 seconds will go up on top and 1 minute goes on the bottom. So canceling those 2 out, I'm in revolutions per minute. So my W of my cam, that should be 15.38. Is that what you get? 3.6? Okay, anybody else? 3.6, is that a better number? 3.8. I'll leave 3.8 just because I'm looking in the book and that's the very same thing that they got, just to be consistent with them. Okay, so this would be the angular velocity of the cam to achieve the total time that we have there on 1 revolution of our cam, okay? Now, the next thing, so we've got our W of our cam done. Now we want to figure out the betas. The betas are the cam revolutions pertaining to each one of the individual prescribed motions, okay? So, for instance, as I said earlier, beta is an angle. So if I say beta 1, that's going to be the angle that the motion for time 1 takes up. Like how many degrees is that in one revolution? All right. So if I have 360 degrees in one revolution, how many of those take up that first motion? Then how many of those take up the second motion, third motion, and so on? Okay. So let's look at, because we want to get that in degrees. All right. So step number 2 now is going to be looking at cam rotation angles. Okay. So beta 1. Beta 1, as we know, is going to be equal to the cam rotation times the time associated with the motion that we're looking at. So we're going to say W cam times time 1, right? Times time 1. Now, we want beta to end up in degrees. Again, how many degrees of a full revolution are we going to be rising our 2 inches in 1.2 seconds? Okay, that's what we're looking at. Now, if we put in 15.28 revolutions per minute and we multiply by 1.2 seconds, we're not going to end up with degrees, right? So we got to kind of figure out how we're gonna deal with that. So cam rotation, or the W of our cam, we had this in revolutions per second, right? So we know that our time is going to be in seconds. So we're going to start there. So we're going to say where W cam is equal to, and we're going to use the equivalent here, the 0.256 revolutions per second. Okay. Now, remember, we want beta in degrees. We want to know how many degrees of a revolution, not how many revolutions are there. So we know that in one revolution, if we put that on the bottom here, how many degrees? 360, right? Revolutions cancel out. So our angular velocity of our cam is going to be equal to what? Is it going to be equal to about 92.16 degrees per second? About? Do you guys get that same number? 92.16 degrees per second, okay? Now, that's the number that we're going to use in this equation here. So beta 1 is going to be equal to 92.16 degrees per second. You could put DEG if that makes sense instead of the little degrees per second. Maybe that looks better. Okay, degrees per second times the time of 1.2 seconds, right? Now seconds are going to cancel top to bottom, and now I'm left with degrees, okay? So you do have to do that little bit of converting to make sure that you end up with degrees for beta 1. So how many degrees do you end up with for beta 1? 110.6? Yep, that sounds good. 110.6 degrees. So we're going to put a little cloud around that because we will refer to that in a little bit, okay? So now we want to do this for each one of our times. So let's do it for time 2. So we're going to do a beta 2, okay? So beta 2 is going to be equal to W cam times T2. And then we're going to take that value that we just determined, the 92.16 degrees per second, and we're going to multiply that times the time 2, which is 0.3. And if you're wondering where I'm getting that from, so step 2 has a time of 0.3. Okay. Seconds. And then seconds cancel. Beta 2. Did you get 27.6? Oopsie. 26.
Yep.
So go ahead and find beta 3, beta 4, and beta 5. Okay. And I know they match the book. So check the answers in the book, but just make sure that you can get each one of their values. So just make sure you get the very same numbers there. Okay. I just kind of wrote the answers out, so. Now, once you get your betas, because we know that those 5 times is our 1 revolution, as a check to make sure that our numbers look good, what we want to do is we want to add them all up to be sure that they add up to 360 degrees. Okay. So once you have your numbers, go ahead and add them up, beta 1 plus 2 plus 3 plus 4 plus 5, and make sure that they add to 360 degrees. Did you check your answers in the book, Jacob?
Yeah.
Okay. Because it's not going to come out exactly, but it's gonna be close. Oh, was it? Okay. Yeah. And that's why you want to check them, because it's a pretty simple calculation to get each one of them. But if it's not right, then your displacement diagram isn't going to be right. So do you guys get about 360 degrees? Wasn't it like 359 point something? 359.422. Yeah, I did it earlier. Yeah. And that's considered 360 degrees. We're good. Okay. All right. So this is truly just a check. Okay, that's just a check before you then start using the numbers. Okay. So any questions about cam rotation, times, and betas? Okay. If there aren't any questions, now, this is what I want you to hand in for this example through this step that we just looked at. So step number 1, finding the cam rotation, and then finding the individual betas, and then making sure that you add them up to about 360 or very close to it. That's all that you have to do for this example. But I'm going to show you the displacement diagram. So in the problem, they wanted you to create a displacement diagram. Now, you will be doing this. The first 2 problems in your assignment are creating displacement diagrams, okay? As I said, for the assignment, you have to do at least one of them, okay? If you're going to take the 40 total points, okay? If you want to do the full 80, then it would be doing both of them, and you're going to create a displacement diagram. So let's look at what a displacement diagram is. A displacement diagram is going to be a graphical representation of the motion of the follower. Okay, the motion of the follower. So if we look at this, you're going to notice that it has a y-axis, a vertical axis, and a horizontal axis. The vertical axis is the follower displacement. So the follower displacement here, the highest point that it went to was a total of 2 inches in that first step, right? So you're going to notice that if we look up here, this is 2 inches, and then the units are 2 inches, all right? So the scale here on the left-hand side is going to be, if you draw, when you draw it in AutoCAD, is going to be however high that displacement is going to be, okay? Along the x-axis, this corresponds to 1 revolution. So you're going to notice that we have a beta 1, right? Okay, then we have a beta 2, beta 3, 4, and 5, adding to an ending of 360 degrees, okay? If we take and we find beta 1, we calculated that to be about 110 degrees. So you're going to notice that it goes just beyond the 90, and they're calling it out here at 110.5 degrees, okay? That's where beta 1 goes to. That is the rise of 2 inches in 1.2 seconds. And that takes 110.5 degrees of cam rotation. Okay. Then our next beta 2 is going to be then this distance. That was a dwell for 0.3 seconds, was it, right? 0.3 seconds. So however many degrees this is, all right, is going to then be the dwell. Notice that at the top here, it ended at 2, and now it's going to stay for that 0.3 seconds, okay? Then the next time 3 was a fall of 1 inch. So this distance right here, it fell. If we measure this, this would be half of the 2 or 1 inch. And then the time that it took is going to be our beta 3, which was 82.94 degrees. Okay. Then it's going to dwell for beta 4. Okay. Beta 4 was 55.3 degrees and it was 0.6 seconds. So notice that it just stays in that position. And then the last portion, it's going to fall one last time back, if you would, to 0 for that total of 2 inches. And then that's going to take us beta 5, the last 82.94 degrees. And then this is 360. So it technically is our 0. And then it starts back over again and goes through the same cycle of, that revolution. Okay. You'll also notice that it correlates to the times down here. All right. What's really more important is the angles, okay, are a bigger deal. That way, if you speed it up or you slow it down, it's more about the angles than it is so much about the time. Does that make sense to everybody? Okay. So displacement diagram, cam rotation angle versus the displacement of the follower at any given time in the rise and then back in the fall. Okay. All right. Let's get back to our PowerPoint and kind of catch ourselves up. So I know I did example 9.1. Now let's look at our follower schemes, okay? Our follower motion schemes. So when we create that displacement diagram, you're going to notice, and I'm going to go back over here. We have some of these curves going, I say, in and out of the motion. And we do want those because that helps to kind of ease in and ease out, okay? So we need to define what is the type of motion for each one of our moves. So whenever we're rising or falling, we need to also say, how are we going to do that, okay? And the how are we going to do it are going to be the motion schemes, okay? So if we go wide variety of motions. Yep. I'm going to jump right in. We're going to go to, I think it makes sense. To look at the first one. So at the top of page 229, we are going to find the follower curves for constant velocity. That's the first type of motion scheme. So when we draw it on our displacement diagram, follower displacement, that's going to be the top diagram that we see here. And this is going to be a rise on the left-hand side, and this is going to be a fall. It's a very simple construction. It's literally a straight line. So we start at 0 and we end at whatever the point is at the top, okay? Now, as we look at velocity, okay? So if we look at, this is our displacement, this is the moving of the cam, and that looks simple, but look at the velocity. The velocity has to be on right away, okay? So if you notice here, if we start at 0 here, all of a sudden we have full velocity from that initial, time that we start. That's not practical, is it? Okay, we have to speed up too. We can't just like put it on. And if we do, we risk our follower not being in contact with our cam, okay, just because it's such a jerky motion, okay? Notice as well that the acceleration is to infinity, okay? So that is not something we want to have. The only time we ever use constant velocity is if it's a very slow moving cam follower arrangement, okay? Under 100 RPMs, okay? That's relatively slow, pretty slow, but anything that gets any higher, you don't want constant velocity. So this is kind of a simple one, but reserved for very low speeds, okay? The next one that we have is called constant acceleration. Now, right away, you can see that when we look at the follower displacement, the top curve in either case, whether it's rising or falling, now we have a curve going in and we have a curve going out, okay? What that's going to do for us is if we look at the velocity, notice now we're ramping up and we're, if you would, accelerating and decelerating, okay? So now it's not as an abrupt start and a stop anymore. And we then don't have as much chance of our follower leaving the surface or the profile of our camp. Okay. So the accelerations don't look amazing, but they're much improved from the first one. Okay. So a little bit higher speed we can use here. And again, because of those curves going in and out. Now, construction of constant acceleration, we are going to see here. I'm going to leave it at that as a diagram because this isn't going to be something that you're going to be using for either of the assignment problems that I have for you, okay? The next two, which are the best ones and the most popular ones, are on your assignment. And those are, the first one is harmonic motion. This is on page 231. The displacement diagrams are here, and you'll notice that again, we have the curves coming in and out. And as we look at the profile of the velocity, again, we see that it's a gradual to its top speed, and then it's going to come back down. And then we also see an improved acceleration curve, okay? So harmonic motion. And then the last one is cycloidal. Again, we've got curves in and out of the motion. We have ramping ups of velocities, and our acceleration curve actually becomes the best on cycloidal, okay? Now, how do we generate these curves? Okay, so going back to harmonic motion, okay? So harmonic motion, what we want to know is how are we going to get each one of these curves going in and out? So that's what we have to construct. We're going to turn the page on page 232 up at the top here. This is how we construct it, okay? So we're going to take our total time and we are going to break it into 6 even segments, okay? Then we're going to look at what is our, in this case, what is our rise? And we're going to take a curve, and at the midpoint of that rise, we're going to do a radius, okay? And now we're going to break that into 6 equal segments, which are 30 degrees between each one of those lines. Then as we rotate around, we are going to line up the 1s, the 2s, the 3s, the 4s, and the 5s, and the 6. And then that's going to create points along that line. Then we're going to use in AutoCAD a spline fit to make the best fit curve through those points. Okay. And that's how we're going to generate it. All right. Now you might say, all right, if I know the height is the easy dimension. Like that's the one that's easy. So if I know that my height is 2 inches, how do I know how long to make like my full displacement diagram? And I'm going to give you a guideline, okay, that I think works really well. They don't give this in the book, so I'm giving it to you here. So on our equation sheet, what we want to do is I'm going to draw a displacement diagram, and this is the total length, okay? So if this is 0 degrees here, and this is 360 degrees, all right? And if we look at 0 degrees here, and this is going to be our total, I'm going to call this H, height, okay? And that's going to be the total rise that we have in our cycle, okay? So in the case of that example that we looked at earlier, that would be 2 inches, okay? The length of your x-axis is going to be 3 times h. That's a really good place to start. So if our rise, our total height was 2 inches in that first problem, we would make our total length here 3 times that height. Okay. If it's 3 inches as our height, then that means that 9 inches for a full revolution is going to be that distance. Okay. I find that that works really well for proportion. What you don't want to happen is that your x-axis gets super long and that your y is short, because then it's gonna be weird. And you also don't want your x to be short and this to be tall. So proportions wise, about 3 times the height for the full length of the displacement diagram seems to work pretty decent. Okay. All right. And we'll use that in the example that we're going to be doing next. So that's harmonic motion. We'll look more closely at that in our example. Cycloidal motion, as I said, this is actually the best one. So when we start getting up into higher speeds, harmonic and cycloidal are the ones that you're going to want to choose. And this is on page 233, down at the bottom here. This is the construction of cycloidal. Okay, so I'm going to kind of briefly go over this. This is going to be something that you'll be doing for one of your homework problems if you choose to do it. And how we set this one up, you're going to notice that we take a full circle. The radius of that circle is going to be equal to the height of the rise or the fall. So however high or low this rise is going to be, you're going to take that and you're going to divide by 2 pi. That's the dimension for the radius of the circle. Okay. Now, at the center of that circle, what you're going to do is you're going to start a line at the end point all the way down. Okay. And you're going to extend it, and that circle is going to go on that end point or along that line. When you determine the length here, okay, this is going to be based on your beta. All right. So once you know, for instance, and we're going to do an example, so we'll go through this. Once you know how long this is, you can figure out what is the dimension of each one of the individual degrees. Okay. You would take this total length, divide by 360, and you would know how long is 1 degree represented along that length, right? When you know what your beta is, then you multiply that beta by the number of lengths in there for however many degrees. And now you're going to have a length of beta 1. Okay. Once you get that length of beta 1 to scale on your displacement diagram, you're going to break that into 6 even segments along that. Okay. And that corresponds to the 6 segments around the full circle here. And then you're going to notice that as you construct 0, 1, 2, 3, 4, 5, and 6, you bring them together in the middle, and then you're going to make your lines parallel to the construction line that aligned that center. Okay. You'll get an opportunity to do this. Don't worry. All right. And if you have any questions, that's what I'm here for. But page 233 is your construction. Okay. So let's look at, we looked at harmonic, we looked at cycloidal. I'm changing up the examples a bit. Okay. What I want to do is the examples here, the first example does not take into consideration harmonic motion, and I do want to show you that. So what I've done is we are going to, instead of looking at example 9.2, we're going to jump to problem. Problem 9.8. Okay, problem 9.8, and this is on page 254. Okay, 254. So let's go underneath here. Now, the reason I picked 9.8 is because it has a harmonic motion, and I want to show you how to construct it. Okay, I want to show you how to construct it. I'm not going to require you to do the AutoCAD here in class. Okay, I trust that you know how to use AutoCAD to make these. Okay, but I want to show you the process that you would go through. All right, so let's do problem 9.8 on page 254. This is going to mimic 9.7 that you have for your homework. Okay, that's why I picked it. So we have a cam. Drive is used for a mechanism that moves a tool in an automated screw machining process. The cam follower must rise outward 24 millimeters with harmonic motion in 0.2 seconds. It's going to dwell for 0.3 seconds. It's going to fall 10 millimeters with harmonic motion in 0.3 seconds, and then it's going to dwell for 0.2 seconds. And then it's going to fall the last 14 millimeters using harmonic motion in 0.2 seconds. And then it's going to repeat that sequence. Determine the required speed of the cam and graphically plot a follower displacement diagram. Okay, so notice for each one of these follower motions, it told us how far it was going, whether it was a rise, fall, or a dwell. It told us how much time it was taking, and then it also told us what type of motion we needed to get there. Okay, and in this case, it's harmonic for each one. Okay, so the first steps that we have to go through before we even get to plotting this is we have to figure out what is the cam rotation speed. We'll do that one right away, the W of the cam, and then we have to figure out all the betas. Okay, so this is going to be problem 9.8. And like I said, I will update the module 8 practice problems to reflect this. So this is problem 9.8. Okay. So what they're giving us in this problem is step number 1. We're going to rise 24 millimeters. Okay. Time 1 is equal to 0.2 seconds. So we have to rise in 0.2 seconds, and we're using harmonic motion. Okay, so kind of like those three things. So we're 24 rise, 24 millimeters rise, a time in 0.2 seconds, and we're going to use harmonic motion to get there. So that's our curves in and out. Okay, the second thing we're going to do is we're going to dwell. Okay, so that means we're not rising or falling. We're staying in the same spot. And we're going to do that. That's going to be time 2, and that's going to be for 0.3 seconds. There's no up or down, so there's no prescribed motion, if you would. Okay. Dwells are easy. Then step number 3, we're going to fall 10 millimeters. And this time, 3 is going to be equal to 0.3 seconds. And we're going to use harmonic motion for that one. Then step number 4, we're going to dwell again. And that time is going to be T4.2 seconds. And then our last step is going to be a fall because we went up 24, we only came down 10. So we've got to fall the last 14 millimeters in T5, of 0.2 seconds. And that is also going to be harmonic. Okay. So we have 5 steps of motion through 1 revolution of that cam. Okay. And notice really we're starting our problem with the end in mind. Remember, the follower is the end result or the output. That's what we're defining the motion for. Now we're going to build a cam that's going to do that. Okay. So step number 1, let's do our angular velocity of our cam right away. We don't need it for the betas, or well, we kind of do, but I like to get it out of the way right away. So W of the cam is going to be equal to, we know that it's 1 revolution per the total time that we're going to take for 1 revolution. Okay. So the total time TI is going to be T1 plus T2, T3, T4, and T5. And we're going to add those together. So 0.2 seconds plus 0.3 seconds, 0.3 seconds, 0.2 seconds, 0.2, oopsie, add my units, S plus 0.2 S, right? I think I got them all. 0.2, 0.3, yeah. So my total time should be 1.2 seconds. Yeah, we've got 6 and 6, 0.6 and 0.6. Okay, so 1.2 seconds. Cam rotation, right? So our W of our cam then is going to be equal to 1 revolution divided by 1.2 seconds, right? And then doing a quick conversion to degrees per second, I know that 1 revolution is equal to 360 degrees. So that's going to cancel out. So my cam rotation that I'm going to use for beta is going to be 300 degrees per second. Make sure you get that same number. So I'll wait. Everybody get 300 degrees per second? Okay, thank you. All right, now what that does is that puts this in perspective for us so that we can now directly use our W and multiply it by the time to get our betas, right? So we know that our beta 1 is going to be equal to the cam rotation times T1, okay? Since this is in now degrees per second, we'll be able to multiply these directly. So we're going to take the 300 degrees per second times our time 1, which is 0.2 seconds. Okay. So our beta 1 is 60 degrees, right? Now we've got to find beta 2 through 5, okay? So beta 2 is going to be our W of our cam times T2, 300 degrees per second. T2 is 0.3 seconds. So our seconds cancel. Beta 2 should come out to 90 degrees. And I'll let you do the rest of them. I don't need to announce each one anymore. I think you guys get it. Since beta 4 and 5 are equal to the same amount of time as beta 1 or time 1, they're all equal to 60 degrees. And then beta 2 and 3 are both 90 degrees, okay? Because they're the same time. So you should get 1, 4, and 5, 60 degrees, and 2 and 3 at 90 degrees, correct? Now that we have all of our betas, we are ready to create our displacement diagram, okay? Now, I'm just going to double check. Is everybody here where I'm at right now? Oh, actually, we should do one thing before we do our displacement diagram. What should that be? Add them up all together. Exactly, David. Add them up all together to be sure that they add to 360. So we just want to say 1 revolution is equal to beta 1 plus beta 2, 3, 4, and 5. So that means we're going to have 60 plus 90 plus 90 plus 60 plus 60. Well, yeah, that's it. Okay. So it looks like we're good, right? We've got 180 plus 180. So 360 equals 360. So that is good. They are equal to each other. Do you have to do this? Yeah, I want you to, because it's so easy when you're doing these. They're very simple calculations. Maybe you forget one on accident. I just want to be sure that you've got good numbers. Okay. So now that we have our betas figured out, the next step is to scale and kind of figure out what we're going to do for the size of our displacement diagram. We already know our overall height is going to be 24 millimeters, right? That's the height from 0 up. Okay. Now, it's pretty darn close to 25, right? So if I'm going to make the length of my displacement diagram 3 times the height, instead of using 24 times 3, I'm going to use 25 times 3 just to make it a nice number. Does that make sense? If you use 24 times 3, that's totally fine. Okay. But I'm going to make mine 25 millimeters. Remember, that's a guideline. That's a place to start. Doesn't have to be perfect. I just picked 75 because to me, 25 times 3 was easier to do in my head than 24 times 3. Okay. That's it. That was it. So any questions about that? So I'm going to go over to AutoCAD now. You do not need to draw this. Okay. You don't need to draw this. I'm just showing you the process. Okay. So my displacement diagram, you're going to notice that my height here is 24 millimeters. Okay. So I drew this in metric. My length is 75 millimeters. Okay. Now, when I did my length down here, I know that this is 75 millimeters, but it also is equal to 360 degrees. It's representing a full revolution. So what I want to know is what is a distance? What is my dimension per degree? So that I can then mark off 60 degrees, 90 degrees, 90 degrees, 60 and 60 over the length to represent beta 1 through 5. Does that make sense to everybody? So how am I going to do that? Any ideas? If I want to know per degree, because this goes from 0 degrees to 360 degrees, and I want to know how much is 1 degree? What is the dimension for that, Jacob? I don't care. I'm going to ask my question first. How am I going to find out? I'll answer your question in just a second. But how am I going to find out what is the distance for 1 degree? If 360 degrees is 75 millimeters, how much is 1 degree? How am I going to figure that out?
You divide 75 by 360.
Yes, so I'm going to take 75 millimeters divided by 360 degrees. So that's millimeters per degree, right? And what do you get for that number? Do you get something like 0.2083 millimeters per degree?
Yeah.
Yeah. So that's what it is for 1 degree. So if I need 60 degrees, right? If I need it to be 60 degrees, if I go back to AutoCAD here, notice that my first chunk, beta 1, that was 60 degrees, right? So if I take 0.2083, multiply it by 60, you should get 12 and a half. Right? Yeah. So that's how you mark off your betas. Okay. Your betas are how much of 360 degrees do I have? Then my 90 degrees, beta 2 was 90 degrees, right? I take 90 times 0.2083 and you should get 18.75. And then I had another 90 degrees, so another 18.75. And then another 60 and another 60. So 12 and a half, 12 and a half. And adding those up, they all add to 75 millimeters. Make sense? Okay. So that's how you kind of scale the length. Okay. So I did my major divisions first for each one of my betas. Jacob, what's your question?
Oh,
How did I get the 75 millimeters? Anybody? Hold on. Hold on. How did I get that? Yes, my height is 24, right? And I said, as a guide, do 3 times whatever your height is, okay? Since 24 to me, in my brain isn't as easy to multiply by 3 as 25 is. I use 25. So that's the only reason I use 75. Yeah. So good question. And this is a guideline. So again, if it's a little shorter, a little bit longer, totally fine, right? But if you want to use a convenient number, kind of like I did, it'll be good. What you don't want to do is I want 24 for my height. And let's say you're like, I'm going to use 1 millimeter per degree. And then you make your x-axis, your horizontal axis, 360 long. Now you're going to get a very like shallow looking curve. Does that make sense? So proportionally, it just doesn't work out. Convenience, it sounds like it's a good idea, but when you start drawing it out, it just doesn't. It's just not. Okay. So use this as a starting point, as a guideline, and it works out pretty good. Okay. And it hasn't failed me yet. All right. Any other questions? So that's where the 75 came from. And then our betas are going to be the multipliers for the distance per degree. Okay. Now let's look at harmonic motion. All right. Here's how we create it. My first chunk here. Okay. I'm going to zoom. I'm going to go up here. My first chunk, my length is 12.5. I need to divide that into 6 even increments. So I simply take 12.5, divide by 6, and then I offset lines that were that even increment apart. Okay, so I've got 6 sections horizontally. Then what I did was I drew a circle center radius for this radius right here. This has a radius of 12, a diameter of 24. You see that? And then this is broken up into 6 even increments. Okay. So because it's 180 degrees, 6 into 180 or 180 divided by 6 is 30 degrees. So 30, 60, 90, 120, 150, and 180. Okay. Now, as we go around clockwise, my 0 starts at the bottom, and then I have my 1, 2, 3, 4, 5, 6. So notice 6 divisions horizontally, 6 divisions around that radius. Okay. Now what I'm going to do is where the 1 crosses that radius, I'm going to take a line and go straight across until I intersect with number 1. So what I literally did was, I'll get rid of this. I just took a line ortho from here perpendicular to that line, and where that intersected, that's the point, okay, that's going to be on. Then I did the same thing with number 2, number 3, number 4. So notice it's division number 3, I'm sorry, division number 4, line number 4. Okay, they correspond, and so on, all the way up to the top. Then to create the spline, all I did was I went under draw. Object line. I went under draw, and all the way over to the left is the spline fit. Okay, so click on that, and then you're going to grab the intersections at each one, and it's going to gradually create your spline through each one of the points. Once you get to the last one, go beyond and then hit enter. Do not hit escape to end the command. Otherwise you'll lose your spline. Okay. I do it all the time. I did it earlier today and I'm like, that's right. So, and then that's how you get your spline along there. Okay. I think we did this for, oh no, we didn't do it yet. We'll do it for the cams as well, the cam profile. Okay. So that's harmonic motion. It's actually pretty simple. Where is it? The more detailed explanation, if you would, is in the chapter on page 232. Okay. So if you go in the book on page 232, it kind of gives you that very same explanation. Okay. Now, the next section here for the next 90 degrees, beta 2, this is a dwell. So all that's going to do is it's going to stay at that top point on my rise, and I'm just going to stay there for 90 degrees. Okay, my beta 2. Then I'm going to fall 10 millimeters, right? So now I'm going to be going this way to the right, my first one is going to be my 0, 1, 2, 3, 4, 5, 6, but now my divisions are over 90 degrees. Okay. So you're going to take 18.75 and you're going to divide by 6 to get your even increments. Then because this is a 10 millimeter height, your radius is going to be 5 millimeters for your circle. And then starting at the top is going to be 0, 1, 2, 3, 4, 5, 6, 30 degrees apart. And then you're going to pull those intersections over and do your spline through the points. Then you're going to dwell 60 degrees. And then you're going to fall the last 14 using that same construction. Okay. Any questions on creating the displacement diagram? And then this would be minimally what you need. I do want to see the construction of, in this case, the harmonic motion. Jacob. These guys? These angles? So remember, it's 6 divisions and it's 6 even divisions on 180 degrees. So 180 divided by 6 is 30 degrees in between. Yep. Good question. Any others? Okay. So again, you guys don't have to draw this, but I wanted to show you this construction. You can always go back and look at it to make sure that you're going to be creating the harmonic motion. This problem is very similar to 9, 7. Is that the one that I have you guys doing? So yes, I have you guys doing 9, 7. So this one is harmonic motion, but it's going to be English units instead of metric. Okay. All right. So what we're going to do is looking at the time, I think this is a good time to take a little bit of a break, and then we'll come back and we will look at one more example. Okay.